This lesson covers an introduction to authentication services. Now, we're going to start with X.500 directory services. Directory services provide authentication services as well as authorization services for a trusted collection of what we call principals. These are users and computers and other objects that we would consider are part of our enterprise, and therefore we have some level of trust with their communications and their requests and access to our valuable resources. So that's what directory services provides. It's a collection of trusted principals that we can authenticate and then authorize to access resources in our trusted environment. And anything outside of our directory services body and implementation, we refer to it as either a realm or a domain. Those are two terms commonly used for this collection of trusted principals. Anything outside of our realm or domain is considered untrusted. And while I say that, most implementations include the ability to establish a trust to a foreign directory services realm or domain. This is implemented through Kerberos. We'll talk about that shortly. So, directory services is all about a collection of trusted objects, the principals, users, computers, and other objects. And this establishes a logical boundary and through software controls a security boundary to isolate these trusted principals from the lesser trusted or untrusted objects outside of this directory services environment. Now, the directory services are implemented most classically in Microsoft's Active Directory domain. And in hardware, where it actually is manifested is in a domain controller. That would be a computer that has a server class operating system installed on it and then has the directory services support installed on that server. So these would be a Windows server of some level with the domain directory services installed on that computer. And that establishes the X.500 directory services environment. To support that Active Directory domain, we have to authenticate these clients carefully. And Kerberos is the protocol or system that we use to support this authentication of these trusted principals to one another. See, this environment might support up to perhaps 1 billion computer users, and that would require a few more than 1 billion computers. We generally assume one workstation per user and then a handful of servers to support the networking infrastructure for file and print services, for the directory services, for name resolution services, for remote access services, etc., etc. So we have to introduce these few billion users to these few billion servers and have them trust one another that they are part of the same trusted domain or realm. And that's where Kerberos helps us. Kerberos uses a key distribution center that, by the way, is implemented once again in these Microsoft domain controllers that support the Active Directory services. So Kerberos is a component that is installed on these same domain controllers. Now, Kerberos is an open standard and also is supported on Unix and Linux systems independent of anything from Microsoft. However, in the enterprise, Microsoft's Active Directory tends to dominate the corporate world, the enterprise solution. For strong authentication and other security services, we get involved in what we call a public key infrastructure that uses digital certificates, X.509 digital certificates. This strengthens authentication and other security services such as encrypted communications channels and encrypted storage. So data in transit and data in storage can be secured using digital certificates. In addition, these digital certificates, as I said, are used to strongly authenticate endpoints. That includes the users, the computers, the servers, and perhaps even domain name services and even routers can be configured with digital certificates. So these digital certificates are used all throughout the networking environment. And I say that they are optional, but they are becoming more and more a standard component in the enterprise environment. Now, to support remote access, which is a commonly needed service in the networking environment, and these would be perhaps users that are telecommuting into the enterprise. They might have web-based applications. They need to access data repositories on the enterprise network. They might be administrators that are managing the infrastructure systems themselves. Things along these lines. They might be wireless computers and users that are using the wireless access points. And they might also be used for authenticating a virtual private network and encrypted channel from perhaps a telecommuting user out on the internet who's connecting into the corporate environment and needs to build a VPN. These are all remote access users. And these remote access users, because they are physically not required to be in the building to connect to our network, they're coming in perhaps over the internet, over a dial-up modem, over the telephone lines, or over a wireless connection. They don't have to be physically in my building to connect into my network. I have less trust for these users, and therefore I need to strongly authenticate them, more strongly than the guy who actually has to come past my security guard, show his ID, his badge, walk through 3 locked doors, sit at a desk with a cubicle surrounded by his coworkers, and if somebody doesn't belong there, those coworkers would recognize that that's a stranger and he shouldn't be sitting at Lulu's desk, and they'll go get the security guard. Because these remote workers don't have to go through those physical access control security controls, I need to more strongly authenticate them, and that's what these next 3 bullets talk about. The first one is remote authentication, dial-in user services, or RADIUS. Now, that's the open standard for strongly authenticating, authorizing, and then auditing or accounting those users' activities. So that's the original implementation. It's an open standard called RADIUS, Remote Authentication Dial-In User Services. Now, Cisco took that open standard and implemented it in a Cisco environment and added a few extra Cisco bells and whistles and interoperability features, and they call theirs TACACS. The new version is called TACACS Plus. That's Terminal Access Controller Access Control Services. And the third version is TACACS Plus. That's a Cisco implementation of RADIUS, essentially. It has a few extra bells and whistles, but typically those are available for Cisco backend as well. It requires a Cisco environment in the backend, so it's a little more proprietary. And then finally, the new remote user authentication service is called Diameter. Now, it's a play on words. They say the second generation of RADIUS is 2 times as good as RADIUS. So 2 times R is diameter. 2 times radius equals diameter. Okay, that's where they came up with this term diameter. So Diameter is the new generation of these authentication services. And Diameter actually has the ability to be implemented in the new cellular 4G networks that haven't yet hit the streets. I know many of you might feel you have a 4G cell phone. There is no 4G today. This is called 4G LTE, long-term evolution. It's not true 4G and does not fully implement Diameter. And so Diameter is the new version of this, enhanced bells and whistles all the way around. And again, its major benefit that it brings into play is support for the 4G cellular networking environment whenever we get to that point. So this is an introduction to authentication services for networking infrastructure. We'll take a break here and pick up where we left off. Picking up where we left off, we're going to look at different authentication protocols. Now, these are placed in more historic order. Some of these early ones are no longer used, but let's look at them anyhow. We're going to start with the password authentication protocol. Even before this very first authentication protocol was introduced, there were network communications that were being established. These were typically done using acoustic couplers, which is essentially a modem. This was done over telephone lines. And in the old days, if you were a guy that had a computer, you're already a champion. And if you were a guy who had a computer and an acoustic coupler and you knew how to use it, you're a really good guy. And if you actually knew the telephone number of another computer that had an acoustic coupler, man, you must certainly be the guy. So back in the earliest days of networking, there was very little need for authentication because access to these systems was so rare, so limited. The only people that had them were the guys that had the legitimate need. They were the intended users. But as these modems got more and more popular and the average Bobo started getting access to a modem, the server side of this, the bulletin board owner, for example, realized the need to authenticate those people that were dialing in and accessing his system and tying up his system. So they introduced first the password authentication protocol. Basically, this was a username and password, but this information was transmitted over the telephone lines in clear text. So if anyone was eavesdropping on that telephone line, which was a possibility, they would clearly be able to decipher the username and password and then would be able to dial in as that user. So this, while it was the first step at authenticating those users, was very non-secure because of this clear text username and password over the wire. Shiba was a manufacturer of modems back in the early days, and they recognized this weakness. So Shiba introduced an encrypted version of password authentication protocol called Shiba's PAP or SPAP. And this used this same username and password, only it used very rudimentary encryption. So now a bad guy would have to eavesdrop on the wire and then crack the encryption. Now, if he was any good, the encryption could be cracked pretty readily. It wasn't very strong encryption. However, for those days, there weren't that many bad guys. There wasn't that much of this hardware around. And as a result, there wasn't much of a threat to the security of this encrypted username and password going over the wire. Now, a better approach to authenticating a user remotely is to avoid having to send those credentials over the wire. That way, if a bad guy is able to eavesdrop on the wire, if I don't ever send the username and password, then the bad guy can't ever steal the username and password. Well, how do you accomplish that? That's where the challenge handshake authentication protocol came into play. So this was a huge improvement over SPAP, and it avoided sending username and password over the hazardous, hostile, vulnerable remote connection. It was referred to as a zero-knowledge proof. Prove to the server that you're the right guy without ever telling the server your password. Yet you could tell him enough that wasn't your password that he knew you knew the password. And so this is called a zero-knowledge proof, and this is the open protocol, challenge handshake authentication protocol. Now, Microsoft, the premier implementer of the corporate environment, MS-CHAP. So they took the open standard challenge handshake authentication protocol, put the proper spin on it, the proper bells and whistles to integrate it into the Microsoft authentication environment, into their domain environment, their implementation of their X.500 directory services environment. And they called this MS-CHAP. And then over time, they improved it. The current version is MS-CHAP version 2. So this is Microsoft's spin on the open standard of CHAP. The open standard of CHAP supported PAP, SPAP, CHAP, and basic authentication, which is clear text, similar to password authentication protocol. But once digital certificates got involved, MS-CHAP couldn't support those. They didn't want to have to rewrite the whole authentication scheme of MS-CHAP, so they added an enhancement called the Extensible Authentication Protocol. Now, what this guy does is it sits on top of MS-CHAP and is basically an application programming interface for authentication services into the MS-CHAP authentication engine. It basically supports any current authentication scheme that isn't natively supported, as long as that authentication scheme, that mechanism, whatever it is written to the EAP application programming interface, the API. So this guy now opens up the authentication mechanism to any current or any conceivable authentication scheme we come up with in the future. And I say for the foreseeable future. 1,000 years from now, it won't be necessary. But as far as we can project into the future, EAP will support these new authentication schemes. And that's what this guy does for us. It says we'll do everything MS Chat version 2 can do, and then anything that is currently written to the API and anything that we figure out in the next decade or 2 or 3 that is also written to the Extensible Authentication Protocol application programming interface. And an example of these EAP-supported authentication protocols includes Cisco's proprietary lightweight EAP utilizing X.509 digital certificates. Now, that digital certificate is used first to authenticate one or both endpoints. That's the server to the client and the client to the server. It then can be used to establish an encrypted channel and SSL tunnel, secure sockets layer tunnel, between the client and the server. And then we can implement additional authentication mechanisms inside the encrypted tunnel. However, this requires more of a Cisco backend to support the lightweight EAP, since it is Cisco proprietary authentication. Microsoft does something extremely similar to lightweight EAP, LEAP, and they call it protected EAP. So this is sort of Microsoft's version of LEAP, only it requires a Microsoft backend talking to Microsoft's Active Directory on the backend. So LEAP and PEEP are two implementations of the Extensible Authentication Protocol into different authentication databases or systems, directory services. We'll take a break here and we'll pick up where we left off later. Let's continue with a look at X.500 directory services as a networking infrastructure service. Now, X.500 directory services was developed by the Telecom division, and their objective was that they recognized there was a need to authenticate and authorize endpoints or users in a large corporate networking environment. As many as 1 billion or so users and as many as 1 billion or so computers. And how would such an authentication and authorization system work with such a large number of users and computers? And in addition, recognize the space that would be required. And I'm talking about around the planet. I'm not talking about a building that would hold 1 billion users or computers, but recognize that this would be a distributed environment, perhaps even a global environment that has to be supported. That's where they came up with this model. X.500 is a standard or a protocol that is a model for how to build a network operating system to support this global networking environment. It might be utilized by large corporations, not the internet, because the internet wouldn't be a trusted environment, but this provides an element of trust for many, many users and computers. So we have to have computers, or a series of servers, if you will, that support this directory services. And these are commonly referred to as domain controllers or directory services servers. In implementation, Microsoft refers to these as domain controllers, Microsoft being the premier implementer of directory services. Today, it's about the only directory services database we use for the enterprise networking environment. Microsoft calls these domain controllers. It supports this distributed database of trusted objects and all the attributes that go along with all these trusted objects. Again, the boundary of what is trusted lives within what we call a domain or a realm, and anything outside that domain or realm is untrusted. So we have these many, many different servers now called domain controllers, again, to support this globally dispersed networking environment. And these servers have to share the same information. In other words, they have to have a common knowledge. So they require synchronization. This is also referred to as replication. So if a user in Oshkosh creates a new user or computer object and adds that to the directory database, that new object in the database, that new information, must be replicated out to all the other domain controllers. And this has to happen fairly quickly so that they all have the same information, so that the system can continue to operate without interruption. We have to have this bidirectional synchronization. We also have to be able to easily administer this environment. So we need administration access. We need to be able to group these objects logically and geographically. And this is typically done with something called organizational units. That's a logical grouping. And we also have a site, which is a physical grouping. And because we may have a different set of security concerns for the users in Oshkosh versus the users in Schenectady. And so we'll have a physical grouping called a site. However, I might have administrators in Oshkosh versus standard users in Oshkosh. And therefore, I would have different OUs to implement different security controls over the administrators, different from those controls over the users. X.500 includes a specially designed protocol called Lightweight Directory Access Protocol. And this is our tool, if you will, to support the communications between the administrators and users and the directory services database. So LDAP is the communications protocol between the various nodes in the directory services environment and the users in that directory services environment, and then the directory services servers, which are called domain controllers. That's LDAP does this. We need authentication services, and we're going to use Kerberos for this authentication service. Kerberos is covered in a different lecture. We'll be talking about that later. And we also need access control services. This is the authorization service. An administrator has more access than a user to the control panels for the different services, but that administrator doesn't need the same access to a database that the user might need. So we have different levels of authorization that are required between the different types of users in this computing environment. So we need access control services. Authorization is one of those components. And the way this commonly gets implemented is through the implementation of rights and permissions. So you can grant rights and permissions at varying levels to varying individuals or groups of individuals. In addition, we need these users to be able to connect to these directory service systems, these domain controllers, and they need to be able to identify where they are. And this is over an IP network, so we need IP connectivity. In other words, we need name resolution services. And in order to support X.500, DNS will be required because DNS has now been enhanced to include what we call service locator records, SRV records. And these SRV records are the various services that support the X.500 directory databases. The way we locate these domain controllers, if you will, are through DNS. And those domain controllers, of course, provide those directory services. And finally, X.500 supports a naming scheme such that we can have billions and billions of objects, each with a unique name in this same trusted environment, and uses a hierarchical naming scheme, including a local host, a domain name, and a top-level domain name, TLD. And classically, these three pieces form what we call a fully qualified domain name. These three pieces then are an essential component of X.500 directory services. Typically, we will know that we're a commercial entity, that's that top-level domain, versus an educational organization like an EDU or military or government, MIL or GOV, that's your top-level domain. And then we'll have what type of commercial entity this is. What's the name of that commercial entity? In my example, we're using Boboville, a commercial entity, boboville.com. We have that domain name and top-level domain. And then finally, we have the server's name. In this case, it's web server 1, and that would be the local host name for that web server that is a member of the trusted entity domain or realm called boboville.com. So using this three-tier hierarchical namespace, I can uniquely name billions of objects. And that's a requirement for X.500 directory services. We'll knock off here for a little while and pick up with the next lesson. This lesson continues with a look at X.500 directory services. Now, X.500 directory services is a model that was introduced by ITUT, the International Telecommunications Union, Telecom Division, and it was first implemented in Banyan Vines. We're talking about late 1980s, early 1990s. Banyan Vines was the first network operating system that utilized this model as their structure, their foundation for their network operating system. Novell followed and called theirs Novell Directory Services, and finally Microsoft came into play in the year 2000 with Windows Server 2000. Now, the Microsoft Active Directory has dominated that network operating system marketplace, and we no longer see Banyan Vines or Novell Directory Services in most environments. It's been pretty well replaced with Microsoft's Active Directory. Now remember, this is a global distributed database with potentially billions of user objects and billions of computer objects, and then dozens or perhaps even hundreds of attributes that must be stored for each of those billion objects. We have a huge database, and it's globally distributed, and it's got bidirectional replication processes to keep those copies of that distributed database synchronized and consistent with their knowledge. Now, the tool that we use to query and access that giant database is a protocol called Lightweight Directory Access Protocol, LDAP. This is the protocol designed to reach into this giant repository of objects and attributes and allows easy access for administrators and users and the different services to communicate amongst the other domain controllers. So LDAP is used commonly within this directory services environment. LDAP uses port 389 to communicate over on the network. Now, the directory services is container-based. It's a hierarchical model or structure with a hierarchical naming space, and based on the groupings, we can apply a common administrative policy. And this administrative policy can be extremely complex and have multiple policies that combine, and some overrule other policies, things along these lines. So these are in implementation generally referred to as group policy objects. This is Microsoft's implementation, and this provides an easy platform. And I say easy, it can get extremely complex, but it is a way for administrators to apply a policy perhaps consistently globally, different policy perhaps from one location to another, different policy for one type of user versus a different type of user. And these establish boundaries and can be used to assign rights and privileges to individuals and to groups and perhaps even to services amongst themselves. A group policy is our primary administrative tool that can be implemented through the directory services interfaces. Now, as I said, the X.500 directory service is a hierarchical structure. As we see here, the triangles shown in this diagram represent the boundary of a namespace. This is also referred to as a domain or a realm, but the objects that live within each triangle are trusted and trusting of all the other objects within that triangle, within that domain, within that realm. And as we see in this diagram, I have 3 different domains, 3 different realms of trust. However, I can build an external trust between 2 of these domains or realms, and I can make it a one-way trust or a two-way trust. In other words, they trust each other with a two-way trust. In implementation, in the Microsoft environment, the two-way trust is the default. So what we see here is a root domain, and basically this domain is very often left empty with just a few administrative accounts and a few administrative computers, servers, if you will, domain controllers. But other than that, this typically remains empty, but it establishes the environment, the enterprise networking environment, directory services environment. And then we spawn a second top-level domain called a root domain. And this first top-level domain is where we might begin to start populating the domain with users and computers and other types of objects. And within that domain, I can build a hierarchical structure for organizational units. And using these different organizational units, I can group computers and users that have something in common relative to the organization. And then I can apply a group policy to that OU. So the policies can be assigned at the domain, the site, or the OU. Site being a physical location, domain is a logical boundary established by a namespace and then enforced by software controls. And then within that namespace, I can further subdivide that with the hierarchical structure of organizational units. And I can link these policies at any of these levels for a very granular level of control. But at the same time, the policy can be applied to hundreds, thousands, even millions of objects with simply linking it at one location. Now, we also see a third domain off to the right, a child domain. This implies a contiguous namespace. So if the top-level domain in this example is called sumco.lan, the child domain would have a contiguous namespace, a subset of sumco.lan, and in this example, we call it child.sumco.lan. The child domain must have this contiguous namespace, but also has the same two-way trust between its parent domain and the child domain. And the trusts in this environment by default in implementation are also associative. In other words, the child domain has a trust relationship with the root domain. The root domain has a trust relationship with the sumco.root domain. And as a result, there is trust between sumco.root and child.sumco.lan. So it's transitive in addition to being the two-way trust that we described. So we'll take a quick break here and we'll pick up with more networking infrastructure shortly. In this lesson, we're continuing with our analysis of X.500 directory services. Remember that this is a distributed database, potentially globally distributed database that stores hundreds, thousands, perhaps even millions, up to perhaps a few billion directory services objects. And users must be able to locate those objects. That's the whole principle behind directory services, is that we have these trusted users and these trusted resources, and the users should be able to locate these resources no matter where they exist. Physically, they exist within this directory services database, and we need to be able to locate these services, these resources, when we need them. The way we locate these resources is through the domain name system, DNS. Within DNS, we populate SRV records, service location records. And as we see in the dialog down below, inside DNS, we have mappings for Kerberos and LDAP in this one example. And we see that these are service location records. And if you look under data, you'll notice that there's a section. One of them is listed as 88. The other is listed as 389. Those are the port numbers that these services use. So Kerberos is going to use port 88 and LDAP is going to use port 389. So when a client is looking for an LDAP server, that would be a domain controller in Windows Active Directory and in implementation. When a client is looking for an LDAP server, the client will query DNS for, in this example, boboville.com, and you'll see that namespace listed over the left-hand side of this dialog. And he will look for an SRV record that uses 389, and that would be an LDAP server. If he's looking for Kerberos for authentication services, he would search the boboville.com namespace for an SRV record that points to 88. That is the port number used by Kerberos services. So DNS is used to locate these X.500 directory services. Continuing on, we're going to look at Kerberos. Now, Kerberos is the authentication system that is used commonly within directory services. So Kerberos provides authentication services, does not provide authorization services. I hear it commonly misstated that Kerberos provides some form of authorization. It does not. Kerberos provides only authentication services between principals in a directory services environment, the trusted realm or domain. Now in Kerberos specifically, they refer to this as a realm. That's the trusted body of principals. Principals are users in computers and other objects that exist within this common namespace, this common realm. So Kerberos uses a third-party component called the key distribution server as the trusted component in the environment. And if the key distribution server authenticates a principal to another principal, because we trust the KDC, each principal can trust that they are actually communicating with the appropriate other trusted principal. So we have a user, for example, and we have a resource server, for example, two principals in a Kerberos realm. Now, these two objects, users and resource servers, will have accounts on the KDC, on the key distribution server, and also this KDC is implemented on a Windows domain controller in implementation in the Active Directory environment. And so these two objects will exist within this domain controller's database. And if the user can authenticate, then the KDC trusts that that user is who he claims to be. His identity is now authenticated. And when a server boots up, it also authenticates to the KDC. And now that resource server has been authenticated by the KDC. So if the user wants to talk to the resource server, he goes and checks with the KDC, and the KDC validates the identity of the resource server, and now the user trusts that he's communicating with the appropriate resource server. And vice versa. When the client actually initiates communications with the resource server validates the user's identity through the KDC, and if the KDC says, yep, that's really that user, then the resource server trusts that that user has been authenticated. And that's where Kerberos stops. Kerberos does not perform authorization. Now, in order to support all these services that we just walked through, we have the key distribution server, may also be called the key distribution center, the KDC. It also runs the authentication service. That's the initial logon for each of these principals. And in order to maintain this authenticated credential, the KDC produces something called tickets. It uses a great deal of encryption, in this case symmetric key encryption, to store securely the information on these tickets. The authenticated credentials for each of the principals are stored on these tickets in an encrypted manner. The KDC produces this ticket and also adds a timestamp to it so that the ticket couldn't be stolen, cracked, modified, re-encrypted, and then used again by a bad guy. The ticket has a timestamp to provide anti-replay protection. If the timestamp has expired, typically the timestamp is good for 5 minutes on a client accessing a resource. Typically that ticket is good for 5 minutes. And that's not enough time for an attacker to steal a ticket, crack the encryption, modify the ticket to say what the bad guy wants it to say, re-encrypt it, and then replay the ticket to the resource server. Okay, this has been a review of some of the services that are provided by the X.500 directory services and an introduction to Kerberos, the authentication protocol used by directory services. We'll take a break here and we'll pick up shortly.